Let's start with a quote from an article that was posted on Archive this week. A key lesson from our analysis is that these constraints apply to the entire landscape, not to isolated regions of moduli space. Holography ties the structure at infinite distance to the physics in the interior, so consistency cannot be checked locally. There's a convergence happening in physics right at this very moment. Lenny Susskind posted a complimentary paper on the Archive November 14th. I'll post links in the description below, but they're learning that lambda cosmology is incompatible with quantum gravity. They're learning that that's the problem. There's a line in Lenny's paper that reads, "The Planck scale emerges as the scale at which the horizon entropy is stored." If the horizon's entropy is stored on the Planck scale, how does it manifest at all scales? I suppose I should provide some sort of definition of the holographic principle before we go any further. The holographic principle is usually described as something like all of the information contained within a volume of space can be described by the data encoded on the boundary of that region. So the holographic principle comes from the fact that black hole entropy scales with its surface area, not the volume. It's counterintuitive. Now, this is shown through the Birkenstein-Hawking entropy equation. Now, this equation tells us that it's the surface area that contains all of the information about the object. This is very odd when you think about it, because surface area is infinitely thin. That is to say, in pure mathematics and pure geometry, in conceptual world, a surface has absolute zero thickness. It's purely a two-dimensional object. But in the physical world, we have general relativity. This means that there is no such thing as an absolute location. All locations are relative to some observer and some horizon. Now, what does this mean? What is a horizon? Horizons are described as the distance of which light becomes unobservable. In our universe, this happens at around 13 billion light years. Now, of course, mainstream cosmology believes this happens because the universe is expanding, but the horizon distance is the same regardless of the redshift interpretation. In other words, instead of expansion, we can interpret the cosmological redshift as gravitational redshift. Now, there's still an observer-dependent horizon. And if you check along R of our coordinates, at any given location, you'll find that the distribution is proportional to 1 over R. And we can use the null geodesics. We don't have to have a coordinate system or a solution to the field equations at all yet. We can just follow the null geodesics and use that as a reference line for our radial coordinate. And like I say, if you check along R, you'll find that the distribution of the density, of the mass density, is going to be proportional to 1 over R. Now, we can fine-tune that for a Hubble constant of 72 kilometers per second per megaparsec. We get a density profile equal to m of r equals 2 pi kr squared. Now, this k is a coupling constant. We'll get to that in a second, but it's important to note that we're working directly with the Hubble constant here. You have to be careful when you're doing this. For one, there's the Doppler interpretation, and there's also 2 different regimes for gravitational redshift. And so, like, if you're not, depending on what equations you're using, you may be off by 2 or 1/2, what have you. You just have to be careful. That's all I can say. Like we're using the real null geodesic equations for gravitational redshift and work directly from the Hubble constant. And so what I mean by that is that you're finding the amount of mass for R directly from the Hubble constant. Regardless, you end up with this mass density profile. Rho of R equals 3K divided by 2R. K is the coupling constant, and it's equal to 0.833 kilograms per meter squared. So where does K come from? Well, from the Hubble constant. But also, at the horizon, there's an amazing numerical alignment. It seems like a coincidence, but it's not. The surface density is exactly 2 times our coupling constant. So it's 1.66 kilograms per meter squared. So this comes from the holographic principle. If you just adhere to the holographic principle on all scales, you automatically obtain the horizon, the Hubble constant, the coupling constant, everything. In mainstream cosmology, they do not believe that the Birkenstein-Hawking equation holds at all scales. This is because they believe the universe is expanding, but it's not. So you can stick with the Birkenstein-Hawking radiation or Hawking entropy equation at all scales. What's amazing about all of this is it's not assumptions, conjecture, assertions, or anything like that. Like there's real equations backing this up, and this is the heart of lots of physical proposals and postulates over time. It's just missing the one piece that the universe is static and not expanding. So the way we can check this is that very near the horizon, Hawking radiation is emitted. Somewhere very, very close to the horizon. At that location, the Z, the gravitational redshift Z, is very high. This means that if you use the standard Hawking radiation equation, the emitted radiation is very cold. It's like 1.4 times 10 to the negative 30 Kelvin. However, because this metric is observer dependent, and this Hawking radiation is emitted from the horizon and not a star, there's a corresponding blue shift. And that's exactly what's needed to obtain the 2.725 Kelvin in the cosmic microwave background. Now, this is remarkable evidence of a static universe. A single parameter is capable of aligning the Hubble constant, the horizon, the surface density, and the CMB temperature without expansion, dark energy, dark matter, or inflation. But it gets better. This distribution allows us to link entropy and energy as well. The scaling is exactly what is needed for the holographic principle. And then let's go back to what we were talking about with surface area earlier. It's very odd that the holographic principle states that all of the information about an object is stored on the surface area because the surface area is infinitely thin. But we should be able to obtain a physical thickness using general relativity. And this is exactly what physicists have been trying to do for the last 100 years or so. They're trying to find an upper and a lower bound to general relativity. Now, it sounds absurd for me to say something like this, but I think I have found a way to do exactly that. At our horizon, the emission location of Hawking radiation is kind of difficult to pin down using mainstream physics. Even the mainstream mechanism behind Hawking radiation is sort of ambiguous in the literature. However, if we tie it to the Hubble constant and assume that it is the cosmic microwave background, we can obtain the emission location for our profile in 72 kilometers per second per megaparsec. The location of emission for our Hawking radiation is 2.15 Planck lengths from the horizon. More than likely, the emission location is probably just 2 Planck lengths, and the Hubble constant is slightly less than 72 kilometers per second. So you got a little bit of fine tuning you can do right there. But this is the minimum length scale because it occurs at the maximum gravitational scale. The maximum Z, the largest Z in the observable universe at that location is the minimum length scale. It's 2 Planck lengths from the horizon. Thus, this gives us granularity to general relativity and an upper and lower bound to infrared and ultraviolet energy scales. In this framework, we can obtain damn near anything with a single parameter. The Hubble constant, the horizon, mass density for a given scale, the angular diameter distance as gravitational lensing, surface density, entropy, BAO, and the CMB temperature are all inextricably connected. Expansion, dark matter, dark energy, inflation are not necessary. There is no Hubble tension, no missing vacuum energy density, no cosmological constant, and no global solution to the field equations. There are no infinite divergences, which means quantum field theory and general relativity are fully compatible.